Now we're going to discuss hydration and hydroboration oxidation reactions dealing with alkynes. Just as in the case with alkenes, we will add hydrogen and a hydroxyl group across a pi bond. And just like with alkenes, acid-catalyzed hydration will form the Markovnikov product. And just with hydroboration oxidation of alkenes, you'll form the anti-Markovnikov product. Again, if you want to look back at the mechanisms for these two reactions, you can check the previous tutorials. So if we apply an acid-catalyzed hydration to our alkyne, we'll see that we will generate the Markovnikov product, where this hydroxyl group is added to the more substituted carbon, this one here. In the case of the hydroboration oxidation, the hydroxyl group is added to the less substituted carbon. There is a catch to this. These two forms, these are called enols because there's an alkene and an alcohol functionality. These two enols do not remain in this form. In fact, they actually change so that we generate a carbonyl group instead of the enol. This is an equilibrium reaction, but it does favor the carbonyl group. This will be the same in the other case. Instead of making a ketone, we'll make this terminal aldehyde. But again, we have a carbonyl group instead of the enol functionality. This is an example of tautomerization, which is interconversion of constitutional isomers with migration of a proton. It's similar to resonance, but this is a constitutional isomer, and a proton does have to move during a tautomerization. Specifically, this is called a keto-enol tautomerization because we're converting between a ketone and an enol. So let's take the first example here, where we have this enol from an acid-catalyzed hydration, and we generate this ketone. So we have our enol and our ketone, so this is keto-enol tautomerization. In this case, because we've got acid in our first step, this will be an acid-catalyzed tautomerization. Why does this occur? A carbonyl group has a stronger bond strength than this alkene. How does this acid-catalyzed tautomerization occur? First, let's draw our enol in the presence of an acid. As we've discussed before, alkenes are sources of electron density, so this alkene can act as a nucleophile and grab the proton from our hydronium. At the same time, we would generate a carbocation, but because our alcohol here has electron density, it has lone pairs as well, this can collapse back down and form the double bond that we're looking for in our final product right here. So now we have this protonated double bond, and we have protonated this alkene carbon here. The next step in our acid-catalyzed tautomerization is we will regenerate our hydronium. The water that's remaining in solution can come grab this extra proton, which will drive some electron density back to the oxygen and eliminate the positive charge. This results in our final ketone product. This mechanism can also be base-catalyzed. So in the example of the hydroboration oxidation, after the oxidation generates the alcohol, we also have hydroxide present, so we can draw this mechanism with a base. How does this work? Well, first let's draw out our alcohol, and again, a base is a proton acceptor. So this will grab the proton here. This bond here can collapse down and generate the carbonyl group that we're looking for right here, and break this alkene bond and put a negative charge on this central carbon. When that occurs, we need to neutralize that negative charge. So in the case of water, we will have the negative charge grab a proton from water, regenerating our hydroxide base catalyst and reprotonating our compound. This will give us our aldehyde functionality. So there are two mechanisms that we have for tautomerization depending on whether you have acid or base present. To summarize, alkynes can undergo acid-catalyzed hydrations or hydroboration oxidation reactions following the same mechanism that you'd see with an alkene. However, enols generated in these reactions will immediately tautomerize to form aldehydes or ketones, depending on which conditions you used above. These tautomerizations can be either acid or base catalyzed depending on the pH of solution.